All right, so today we're going to talk about types of chemical reactions. Types of chemical reactions is going to be an important topic because it allows us to categorize different types of reactions into usually what are considered one of five different categories. And this allows us to find some commonalities between them. It allows us to figure out what's going on in any given reaction. And most importantly, it allows us to make some predictions. For example, if we take any two reactants and we pair them up, based on the pairing, it should allow us to figure out what type of reaction would that be if they did react. And then knowing that and knowing how these different types of reactions work, we can actually start to predict what are the different products going to be. And this is useful for a lot of reasons, but obviously it allows you to figure out, is the reaction you're going to do going to get you the product that you want? Or sometimes you don't want things to react, you want them to be stable. So, making sure that you're not putting two things together that would react when you obviously don't want them to. So as we begin, reactions themselves fall into two broad categories first. We have what are called reduction and oxidation reactions. Those are usually referred to as redox as a shorthand term. Redox reactions are characterized by the changing in the way the electrons are shared or distributed between different elements and molecules. We know that a chemical change occurs when the bonding is changed, so redox reactions are directly related to that. One of the elements or molecules or species is obviously going to be gaining some electrons, or sometimes it just means that it's forming additional bonds, and as a result, something else is going to have to lose them. Now, within that one category, there's a couple different subtypes, and it's those subtypes that allow us to predict what the products are going to be or how they're going to interact. And we're going to go through the subtypes in a lot more detail to follow in the next series of videos as we go through. But those subtypes would be synthesis reactions, combustion reactions, decomposition, and then what are called single replacement. Now, there are also some non-redox reactions where there is no direct change in the electrons being distributed. However, what happens here is this is usually occurring between two different ionic compounds, and it has to do with the Coulombic forces between the ions, where the cations and the anions of one compound interact with the cations and anions of another compound and end up redistributing. They end up repairing up where the cations go with different anions and so forth. Now, we're going to talk more about redox reactions to start because there's more different subtypes in there. So redox reaction is, like I said, when an electron is gained or lost by one of the species, leading to what we call one of this chemical species being oxidized when it loses an electron, whereas the other chemical species that gains it is going to be reduced. This is often remembered by the mnemonic phrase, Leo goes Gur. So losing electrons is oxidized or oxidation, gaining electrons is reduction. So if we look at our example here of two sodium atoms combining with one molecule of chlorine gas to form 2 units of sodium chloride. If we look closely at what's going on in that reaction, let's pull up my pen here. Here in this, at the start here, this sodium atom has no charge. Right? It's neutral, it's elemental sodium. And same thing here for my chlorine. This is elemental gas and has no charge. However, in my product, we know that sodium as an ion is going to have a positive 1 charge, and chlorine as an ion is going to have a negative 1 charge. So from the beginning of the reaction to the end, the sodium has lost an electron, and from the beginning of the reaction to the end, the chlorine must have gained an electron. So in this case, right, Leo goes Gur, losing electrons is oxidized. The sodium atom must have been oxidized, whereas the chlorine atom was reduced. And usually we say then that the sodium atom was oxidized by chlorine, so chlorine is the oxidizing agent, and chlorine became reduced because sodium reduced it. This is a little bit easier to see with different ionic reactions like this because we know that they have charges. But what about examples where we don't actually have ions? Right, here's an example of a reaction between carbon tetrahydride and oxygen gas to form carbon dioxide and water. Now here, there are no ions, but this is still a redox reaction. There's still a change of charges and charges and electrons between them as new bonds are formed and things change. So tracking the oxidation states in these types of reactions becomes a tool that chemists use to track them and figure out what's going on by talking about what would the charges be if they had to have a charge. So this is a tool. It's not imaginary, but it is not an actual charge. It is just something that we're working with. Now, for example, what I mean by that is if we look first here at carbon and hydrogen in this compound, we know that this is a covalent bond. There's no ions here. However, we know that carbon on the periodic table compared to hydrogen, carbon has a much greater attraction with its extra electrons. So if it had to make a charge, we know that carbon would be pulling the electrons from the hydrogen, and each of these hydrogens would lose one of them if it could, because hydrogen only has one electron. So here, that means carbon would have to be gaining 4 of them if this were an ionic compound. Our oxygen here, as an element, would have no charge. It's not gaining or losing anything with itself. In our products, we know that as an ion, oxygen would always be losing 2 of them, 2 minus, but since there's 2 oxygen atoms in that means the carbon in this case would have to be 4 positive to compensate. And then over here on our water, now our oxygen again 2 minus, which means that we would have to have 2 plus. Well, technically it would be 1 plus for each of them, but there are 2 of them. So if we look at how the different atoms in these molecules changed over the course of the reaction, carbon went from 4 minus to 4 positive. And we had oxygen go from 0 to -2. If you add up all of the different oxygens, it amounts to the same amount of oxygens on the left side, so the reaction itself is balanced. But here, our carbon atom changed. It went from -4 to +4. The only way it could do that, right, if it were an ion, would be by losing lots and lots and lots of electrons, specifically 8 of them. So here we're losing electrons, whereas our oxygen, it went from a neutral 0 charge to a -2 for each of those. So that would have had to gain electrons. So again, Leo goes stir. Losing electrons is oxidation. So in this case, the carbon atom in those molecules had to have been oxidized, whereas the oxygen atom in the original oxygen gas was reduced by the carbon. So within the different redox reactions, there's the 4 subtypes: synthesis, decomposition, combustion, and single replacement. We're going to look specifically at each of those, but if in terms of the video we just did, the first reaction with sodium and chlorine was an example of a synthesis reaction, and then the previous example with the carbon tetrahydride was a combustion. But we're going to look more at the mechanisms of each of those, how it ties into redox, and the energy changes associated with all of them.